Hello, everyone. What we're going to do in this video is prove and we'll talk about Chebychev's inequality, a nice consequence of this that's on the latest prelim, and prove and state the really foundational Fatou's lemma. Okay. So to prove Fatou's lemma, we're going to need Chebychev's inequality. So what is Chebychev's inequality? Uh, It's actually very similar to the probability inequality that most of us probably know. Sorry, not theorem, but inequality. Okay, so it's a very straightforward inequality. Let's say, as always, E is going to be measurable throughout this lecture. So let's say we have a measurable function, non-negative. If lambda is bigger than 0, then the measure of this set here, set of all x and e, where f of x greater than lambda is less than or equal to 1 over lambda times the integral of f over e. So, yeah, I will do this same way the book does. The kind of in the I think it's like page 387 or something like that. Where it does this towards the end. And really you can prove this just using the definition of this integral here. So what's the proof? As typical of any proof of Chebychev's theorem, let's give this a name. Sorry, bigger than lambda. Okay, so let's pick a very, very, very simple function. Particularly just lambda times the characteristic function of E lambda. Okay, and we're going to consider this as a characteristic function over E. Okay. So I claim that clearly lambda is positive, so this here is non-negative, but I claim it's less than or equal to f. Okay, so how do I prove that it's less than or equal to f? Well, we just look at two cases. Let's assume yeah, sorry. Yeah, so let's assume brain fart there. Let's assume x is in E lambda. Well, then just definition, characteristic function. This is lambda, and this is less than f of x, where we're using the fact that here we're using the fact that x is in E lambda instead of all x and E, where f of x is less than, sorry, f of x is bigger than lambda. Okay. And, well, trivially, if x is an E, take away E lambda, then, well, this is 0. Oops. All right, so if you recall the definition of the Lebesgue integral of a non-negative measurable function, this is very useful. So the conclusion is that this is between 0 and f on E, and in particular also this is a simple function. So I'll just remind you of the definition, the integral of f over E. Okay, so remember these two dots mean the definition. And I'll use this var phi tilde, because I want to particularly use this phi here. So this is a premium of all these integrals, or integrals of simple functions between 0 and f on E. All right. Okay, well, yeah, soup is, well, an upper bound of all of these integrals, so we have a particular integral in mind, integrating var phi here, what we described a moment ago, right here. Okay, so yeah, as an upper bound, this is bigger or equal to well, this is just lambda times its characteristic function. So that's going to just be lambda times the measure of lambda. And well, that proves it. The measure of E lambda is less than or equal to 1 over lambda times this integral here. So a nice little easy proof. All right, so a nice consequence of this is actually a prelim problem from the latest prelim, or either the latest or June 2023, forget which. But yeah, a very straightforward application. An example of how to use Chebychev's theorem is as follows. So a little proposition here. Yeah, so if I have a measurable non-negative function, of course, E is measurable, F is measurable also. So if this satisfies this integral equals 0, maybe make it a little clearer, then f of x particularly equals 0. The best we can say is for almost every x. All right. Okay, so the proof is very easy. Okay. Let's look at this set here. Set of all x, where f of x is positive. Okay. We want to prove that this has measure 0. So then f of x will be 0 for almost every x. The set of all x where this here is false has measure 0. This is a set right here that I'm putting in blue. This is a set of all x where this, what I haven't read, is false. So we got to prove that this has measure 0. And that's pretty easy. So we can't use Chebychev's theorem with lambda 0, unfortunately. But we do the next best thing and do the obvious kind of next thing. Well, f of x is bigger than 0 precisely when f of x is bigger than 1 over n for some natural number n. Okay. And we use Chebychev's theorem on each of these. So this is kind of trivial here. So sorry, I need the measure of this. Okay, so these sets are equal, so obviously the measures are equal. And f is assumed to be measurable, so this is the countable union of measurable sets. Right. So actually these are going to be nested. These are, sorry, ascending. They're definitely ascending. In particular, if f of x is bigger than 1 over n, then it's certainly bigger than 1 over n plus 1, bigger than 1 over n plus 2, etc., etc. So these sets are getting bigger and bigger and bigger. Or you can use countable subadditivity, really doesn't matter which one you use. Well, I'll just use, because we do get equality. By continuity of measure, this is equal to this limit here. And now we will use Chebychev's inequality. Sorry. I'll use n, that it matters, but okay. So now we use Chebychev's inequality. So this is less than or equal to 1 over n integral e of f. Now, of course, 1 over is n. That could be very large. Sorry, I forgot the limit. But our assumption is that this right here is 0, right? So very simply, this is n times 0. It's a little funky, so I'll just do x here. X for multiplication. Well, that's 0. And that basically, however you write it. So these two brackets, doesn't matter. It's looks like no, but whatever. N times 0 equals 0. And that's it. There's really not much more to it than that. Okay, what I would like to do quickly now is briefly introduce the subtlety of of interchanging limits and integrals. So one nice aspect about the Lebesgue integral is as follows. So if you remember from real analysis, undergraduate or the kind of the course before this, you can definitely have Riemann integrable functions that do not converge pointwise to a Riemann integrable function. So for example, let's say Fn of x, let's say all these are on 0 to 1. Let's say, sorry, before I do that, let's say I enumerate all the rationals in 0 to 1 as R1, R2, etc., etc. Okay, so let's say this is 0, or so let's do it 1. If x is in R1 through Rn, 0 otherwise. Okay. So yeah, this is Riemann integrable, and certainly this is 0 because it is well, it's 0 everywhere on 0 to 1 except for finite number of points. So obviously, and this is what I have here is for each n. Okay. So then obviously this limit is 0. On the other hand, this is going to be f of x. Where this is just going to be, so this is the typically called a Dirichlet function. So it's 1 if x is rational, and 0 to 1, 0 if x is irrational, right. So the point here is, doesn't even make sense to take the integral of 0 to 1, or the integral from 0 to 1 of f in the Riemann integral sense. So this is not Riemann integrable. All right, yeah, so we simply just, we don't have this issue for the Lebesgue integral. Okay? Why? As long as we're dealing with measurable functions, so let's say these are extended non-negative real valued measurable functions. And certainly here, everything is non-negative here. It's either 0 or 1. So we're dealing with non-negative functions. So if each one of these is measurable, and this limit here point-wise, almost everywhere, E is assumed to be measurable, then F is measurable. And so everything we've proved about integration of a non-negative function applies to f. So there's no issue with whether we can integrate f or not, and whether the basic properties of integration hold for f. Okay. On the other hand, the question, and we're just going to pose this question for non-negative functions because we haven't even defined integration for more general functions yet. So the question is, just like before, if Fn converges to F, so here Fn is non-negative measurable function on E. Or forget about almost everywhere. What about just we have pointwise convergence on E? So if we have this, any answer is pretty clearly no. So I'll do a whole bunch of examples. Yeah, so let's do maybe this absolutely simplest example you could imagine. So let's say E is R and Fn of X is 1 over n times the characteristic function. Well, sorry, let's say it's a constant on yeah, let's just say it's just this constant here. Obviously, this goes to 0. Right? Yeah, that's obviously trivial. Okay, it's uniformly convergent on R, obviously. But because here R has infinite measure, E so as I mentioned many times, you integrate 0, you get 0. Just I mean, yeah, just by definition. Okay, so certainly this limit, which is infinity, is not equal to 0. And you might grumble, well, this is kind of, I don't like this example because, well, this has infinite measure. Fair enough. All right, so let me provide you a different example. So let's say Fn of X, so sorry, let's say E is 0 to 1. So I want to point out, yeah, you have convergence for any X in R. So let's say E is 0 to 1. And let's say Fn of X is going to be, this is a cool example because it kind of leads to the idea of a Dirac delta function, which is not done in this course, but I do have a whole, at least one full video on Dirac delta functions and approximations of the identity in my harmonic analysis playlist. And I will do that in my AMAT 612 course in the fall 2024. But anyway, so let's say this is n times the characteristic function of let's do it this way, 0 to 1 over n. Doesn't matter if it's open or closed. But I want this to be open. All right, so the graph here is pretty clear. It's not drawn to scale, obviously, but that's fine. Right, so it's 0 at 0. Maybe I'll do the graph here in lavender. So Of course, it doesn't do that. That's fine. So it's going to be a circle here. Okay, so another circle. Can't really see that color too well, but that's fine. Yeah, so this is the graph. So here is 1, and this is n. Okay, so right, so easy exercise. This converges to 0 for every x in 0 to 1. I mean, well, why? Well, pick an x bigger than 0. So let's say we have x right here, and just pick n larger than x, then fn of x is 0. On the other hand, if you have x is 0, well, fn of 0 is always 0, because 0 is not an open 0, 1 over n. So no matter, those, we handled the two necessary cases. Either x is 0 or x is strictly bigger than 0 and less than or equal to 1. Okay. So let's say this is f of x. So this is 0 because this is the 0 function. Well, trivially, this is integrate this simple function here, just base times height, or just measure. This is 1 over n. This is n. Well, that's just 1. Yeah, so you might grumble, well, this is unbounded, and so that's what screws things up. Well, on the real line, I'll give you a similar example, or sorry, not similar. I'll give you an example where you have a bounded function that bounded sequence of functions converging to 0, where you can't interchange limits and integrals. Now, if E has finite measure and the sequence of functions are bounded, then you can interchange limits and integrals. And we'll prove that that'll be an easy consequence of the Lebesgue-dominated convergence theorem. So I want to repeat that again. If you have a sequence of functions that is bounded on a set E of finite measure, so you even just need bounded almost everywhere, uniformly bounded almost everywhere, then absolutely you can interchange limits and integrals. The limit of the integral of my fn's is the integral of the limit of my fn's. That'll be a consequence of the dominated convergence theorem. Yeah, and of course, if I had something like squared here, this is still true, whereas this would, of course, be, well, infinity, trivially. N squared times 1 over n. That's infinity, because, well, this obviously isn't. Okay, yeah, so one more example. Yeah, so let's say E here is 0 to infinity. Let's say this is a characteristic function of n to n plus 1. Okay. Yeah, the graph here is pretty trivial. So let's say this is 1 here. Endpoints really don't matter. I'll do lavender again. So open here, open here. Right. So yeah, trivially, like before, so for any n, sorry, for any x between 0 and infinity. But yeah, just like before, this limit here is going to be 0, just kind of trivially because pick an x and then pick an n bigger than x. Then this is 0. Certainly not uniformly convergent to 0 on R, but it's fine. Yeah, so you integrate the limit function to 0. Yeah, so this here, silly here, 0. In definition, because 0 times infinity is 0. This is 0. Well, this here, just trivially is going to be 1. Just because, well, the area under these are all going to be 1. Oops. Keep forgetting I don't use the whiteboard here too much on Zoom. Right, yeah, because each one of these equals 1. On the other hand, I could, again, modify this to be, let's say, instead of 1, let's say stick an n here. So this would be n squared or whatever. Right, still, the limit function is 0 because, again, you pick an x. For any x between 0 and infinity, just simply pick an n bigger than x, and then fn of x is 0. On the other hand, this is 1, n plus 1 minus 1, the length of this interval, times n. This would be infinity. Because this is going to be n. So this would be infinity. Right. And you can make other silly examples, kind of, like these get tall and skinny, and there's a lot of little silly variations of these examples, but the whole point is, yeah, it's a subtle question. So yeah, we've given multiple examples to illustrate the answer is no. So the real question is, when can you? So yeah, this is the real question. Sorry. So let's just get rid of this. Yeah, so this is the question. And we'll spend a lot of time going over that, particularly the beginning of answering this question is what I'm going to do next, is Fatu's lemma, which is an incredibly powerful tool. extremely general, extremely useful. And then we'll do the monotone convergence theorem, and then Lebesgue dominate convergence theorem. And there are some more obscure types of theorems regarding this question, like Vitali's convergence theorem. The same Vitali who came up with the existence of a non-measurable set. But generally speaking, those three, monotone convergence theorem, Fatou's lemma, Lebesgue dominate convergence theorem, they basically handle any kind of interchange of limits. They handle the vast majority of interchange of limits kind of questions that you'll see. So, okay, yeah, next up is a proof and statement of the very deep Fatou's lemma.